Today we're going to talk about using the continuity equation to calculate out the aortic valve area. Now the continuity equation deals with the conservation of flow. And mathematically we would write the continuity equation that flow at one point in an enclosed system has to equal flow at a second point in that enclosed system. Taking that one step further, we calculate out flow in a system as the cross-sectional area of 1 times the time velocity integral of 1 has to equal the cross-sectional area in the second point times the time velocity integral at the second point. So we've simply taken our formula and broken it down into its components. Now looking over here to the right, the components that we're talking about is flow in the LVOT. So flow in the LVOT is flow 1, and flow through this narrowed aortic valve is flow 2. So whatever the flow is going through the LVOT has to equal the flow through the narrowed aortic valve. So we're going to go back to our equation here, and really what we're going to try to solve for is this cross-sectional area 2. Mathematically, to do that, all we really have to do is divide this side by the time velocity integral of 2 and divide this side by the time velocity integral of 2, and that makes these cancel out. And now let's rewrite this. And since we're calling this the aortic valve area, let's say that the aortic valve area, which we were calling cross-sectional area 2, is going to be equal to the cross-sectional area of the LVOT times the time velocity integral of the LVOT divided by the time velocity integral of the aortic valve. So that's how we manipulate our equation to solve for the aortic valve area. Now let's talk about these other components. First, we need the cross-sectional area of the LVOT. Well, that's very simple because the cross-sectional area, or the area of a circle, is simply equal to the diameter of that circle squared times 0.785. Now, of course, you can also use that the area of a circle equals pi r squared, but I like this formula and that's the one that I use. The other thing that we need to talk about is the time velocity integral. So what is the time velocity integral? Let's say that we have a tube, maybe a blood vessel. Here's our blood vessel. And at some point in that blood vessel we have a red blood cell. Now each time that the heart contracts and pushes blood out, this red blood cell is displaced. And the time velocity integral represents the distance that a blood cell is displaced each time the heart beats. So it's really just representing this distance here. Now how do we calculate it? We calculate it from our Doppler flows, either our pulsed wave Doppler flow or our continuous wave Doppler flow. But this little pattern here represents a pulsed wave Doppler flow tracing from the left ventricular outflow tract. And all that we really need to do is take our calipers and trace this little envelope of flow. And it's going to give us a number. That number is going to be a unit of distance because we said time velocity integral represents the distance a red blood cell travels with each heartbeat. So in this case, our pulsed wave tracing that we obtained at the left ventricular outflow tract has a time velocity integral of 15, and then using continuous wave Doppler through the aortic valve, if we trace this, you see you get a much larger time velocity integral of 60 centimeters. So what we have to do is go back to our LVOT and we're going to measure the diameter of the LVOT. So we're going to set a caliper there and we're going to set a caliper here, and we are going to get the diameter of the left ventricular outflow tract. And let's say that in this particular case that diameter is 2 centimeters. So we've got our diameter here that we can calculate out our area with, and we have our time velocity integral both of the LVOT and of the through the aortic valve. So let's go back to calculating here. We said that cross-sectional area, or area, is equal to diameter squared times 0.785. So we'll take our diameter, which we said was 2 centimeters, and we'll square that, and we'll multiply it times 0.785. And so what does that give us? That gives us 3.14 centimeters squared. So now we've got our cross-sectional area. This is of the LVOT. And we've got our time velocity integral of the LVOT, our time velocity integral through the aortic valve. We've got everything that we need. We can just come back to our formula and say that aortic valve area is equal to the cross-sectional area of the LVOT, which was 3.14 square centimeters, times the TVI of the LVOT, which we said was 15 centimeters, and the TVI through the aortic valve, which we said was 60 centimeters. Now we simply do our math. Our units here are going to cancel. 15 divided by 60 gives us 0.25. Multiplied times 3.14 gives us an aortic valve area that's equal to 0.79 centimeters squared. So that's our aortic valve area. Now, the other thing that we can do here, making this maybe even just a little bit simpler, is we can substitute velocity for time velocity integral. So we can also say that the aortic valve area is equal to the cross-sectional area of the LVOT times the velocity of the LVOT divided by the velocity of the aortic valve. And on my tracings over here, I've written out some velocities. I will say the velocity at the LVOT is 1 meter per second. Velocity through the aortic valve is 4 meters per second. So we just say that the aortic valve area is equal to the cross-sectional area of the LVOT, that was 3.14 centimeters, times the velocity of the aortic valve, 1 meter per second, divided by the velocity of the aortic valve, which is 4 meters per second. Mathematically, this 1 divided by 4 gives us 0.25. 0.25 times 3.14 also gives us an aortic valve area that is equal to 0.79 centimeters squared. So here's two different ways that we've talked about being able to calculate out aortic valve area. One is using time velocity integrals, and in that case we got 0.79 centimeters squared. The other is using velocities, and we also got 0.79 centimeters squared.